right, here we go. All right, great to be here. Yes, enjoyed EuroRust last year. Very glad to be back. We are talking about writing an SD card driver in Rust. Hands up who saw my Rust Conf talk in Montreal a few weeks ago? Not many. New audience. Excellent. A few hands up. I did offer to do this talk at 640 by 480 like I did my last one, and I was told it was an unusual and non-standard resolution. I mean, I might beg to differ. It was the standard, but anyway, I've done my slides in PowerPoint 2024 instead of PowerPoint 95, which means you get to suffer through slide transitions. I mean, suck it up. Microsoft gave me the button, I clicked on it, we're going to go with it. So, I am a full-time Rust trainer, software engineer at Ferrous Systems, used to be on the Leadership Council, used to be on the Embedded Devices Working Group, and I've written things in embedded Rust. I've always tried to push the boundary of what's possible in embedded Rust. There's a website, various GitHub repositories, you can find me. But to talk about SD card drivers, we first need to talk about what an SD card is, which is the part of the talk where I give you the computer history lecture. If you're watching on YouTube, you can skip to about halfway, and that's where the Rust starts. The rest of you, we're going to talk about SD cards, and they are old. 25 years we have had the SD card. They are older than floppy disks were when SD cards came out. And over the years, we've had different sizes. No one's ever seen a mini SD card. I mean, they're in the standard, but they're weird. You normally see the full-size SD card. That's the one that'll maybe go in your camera. And the micro SD card, which is the one that you regularly lose, which is why you put it in the adapter and then put it in the full-size SD card slot. The original cards were SD standard capacity. We've sort of call those SD-SC now. They went up to 2 gigabytes. Then there were the high capacity cards that go up to 32 gigabytes. And then you have the extra capacity and, I guess, ultra capacity for the incredibly large cards. I'm generally focusing on the earlier ones because I want to use it with a microcontroller. Now, to use SD cards, you need to look at the specification. You and I are mere mortals, and we are unable to look at the SD card specification because you must be members of the SD card association to read it. However, they do provide a thing called the simplified specification. This is kind of a subset of the standard, and this is enough to kind of write a basic SD card driver. You can just kind of Google for SD card specification and various copies will turn up. This one's from 2017. It was fine for my purposes. Within that specification, it talks about 3 kinds of bus protocol. There are different ways to talk to your SD card. The SD bus, the SPI bus, and a thing called the UHS-2 bus. Well, that first one, that's the thing your Raspberry Pi is going to use. Your Raspberry Pi 3, 4, 5, and whatever. It's a 4-bit wide bus, and you can go up to maybe 100 megabytes a second. You may have seen recently Raspberry Pi announced a line of SD cards, and they've changed the way the driver works in Linux. But that's the kind of the standard interface, and you can't use it on a microcontroller because you need access to the spec, and it's complicated. So what I'm focusing on is the SPI bus version of the spec. This is a 1-bit wide bus. There's 1 bit in and 1 bit out. It's full duplex, and it's much easier to drive from a microcontroller, and it's fully explained in the spec. And then the UHS-2, I mean, look at this absolute unit. They've just snuck extra pins in. It does low voltage differential signaling. It's wild. And it gets worse. Here is a copy of the SD Card Association website, and yeah, that UHS-2 card is only 2013. They keep changing the spec. They keep publishing new versions. Up at the top there, SD cards that talk over PCI Express with trusted compute and goodness knows what. The good news is we can ignore almost all of that. Basic SD cards will just work in the basic mode. And yeah, we can ignore almost all of that. So what is an SD card? An SD card is a computer, and we use it for storing files, and an SD card has literally no idea what a file is. It just stores bytes. So how do we kind of tackle this problem? Well, this gives me an excuse to talk about my second favorite topic, which is systems engineering. And so we tackle big problems by dividing them into smaller, manageable pieces. And then we define nice, clear abstractions between each piece. And this is how we understand it. And I think of it like a stack of pancakes. We have different layers in our system. And at every layer, you think about what services do I offer to the layer above, and what services do I consume from the layer below. And then we can, test our layers in isolation. We can give them some fake requests from above, and we can listen to the messages they send out below. On some systems, the layers may just be function calls. They may just be code in different modules. They may be methods on different types. I guess if you're a web developer, each of these might be a pod, some kind of Docker container, microservices thing, sure, whatever. For me, they're just function calls. We can just send messages down by placing a function call, and then eventually we get the response back. So for SD cards, these are the kind of concepts we need to think about, and this is how they are layered. So at the top level, we need to think about files and directories. This is what the user is interested in. I want to look in a directory and see what files I have, and then I want to open those files and look at their contents. But the next layer below, the thing the SD card is mainly concerned with, is the idea of a block. Typically 512-byte unit of data. Some systems now have 4K blocks instead, but a file system at the top just needs to talk in terms of blocks to whatever layer comes below it. When we write an SD card driver, we need to turn those requests for blocks into SD card commands. The protocol defines a set of commands we can send to the card, and then we can get responses back. But those commands need to be actually sent to the SD card. So then we get into sending bytes over SPI, which is how we talk to the card itself. But we can break these apart, kind of test them in isolation, put them back together, and then hopefully we get a working system. And so you might call these the file system API, the block device API, the command API, and then at the bottom level, we're going to talk about the embedded-hal and how that provides a consistent interface for talking to SPI devices, regardless of the kind of microcontroller you've got. And to talk about these, I'm going to start arbitrarily in the middle, and we're going to start talking about block devices. The history of the block is really interesting to me. Again, we're continuing on the computer science history lecture. In the old days, we had floppy disks, right? We've got the 8-inch, the 5¼ inch, and the 3½-inch. And you would locate a piece of information on this two-dimensional circular surface with what's called the cylinder, the head, and the sector. So the head could move in and out, and these disks would spin, and that would give you access to one sort of infinitely repeating loop of magnetic media, and that's known as the cylinder. And then you choose which read and write head you want to use, either the top of the disk or the bottom, or if you've got a fixed disk, also known as a hard disk, then you may have multiple platters, and then you've got multiple heads to choose from. And then within that kind of infinite repeating ring, you need to divide it up into sectors. And on that magnetic media, you need to store special magnetic sequence that indicates this is the start of sector number 3, and then you encode the data, and then you need some kind of checksums at the end to say, yeah, did you read the sector correctly? Because floppy disks are unreliable. And this is relevant because this is how SD cards kind of work. They're still built on this block idea. That sector you read from the track is now what we call a block. In sort of the mid-1980s, into the 1990s, the idea of using the cylinder head and sector, if you've had an old-fashioned PC, you might have typed in those CHS values. That kind of went away, and we switched to what's called a logical block address. So all of the blocks on the disk, we now just number from 0 up to however many blocks we have available, and that's the interface that SD cards use. It's also the interface that USB thumb drives use, SATA drives, NVMe. They're all about giving you access to a specific numbered block. You say, I would like block 67, and it gives you the contents of block 67. Now, SD cards, I said they're a computer, and they are. And here is a picture of a USB thumb drive, very similar kind of idea, but the thumb drive slightly bigger so we can see what is going on. Inside, there is a NAND flash chip. And the reason we don't just use NAND flash for our storage is that it's complicated, right? NAND flash is cheap, and the trade-off is it's complicated to access. When you write to a page in a NAND flash, you can only write to pages that are blank. And if you wish to erase one of those pages, if you were to make it blank, you actually end up erasing 64 of them at once. So you can imagine, if you just want to say, I'd like to write block 0, that's a problem because maybe blocks 1 to 63 already have some stuff in them and you don't want to be erasing that. And that's the job of the processor. The processor sits in front, it receives the instruction, hey, please write this to block 1, and the processor will pick somewhere in the NAND flash that hasn't been used and store the data there. And if you keep rewriting to the same block, your data will get written to different parts of the NAND flash. The processor is just hiding that from you and moving things around, which is also why formatting an SD card or a thumb drive doesn't really delete anything, because your data is not where you think it is. It's just been randomly spread out across this NAND flash chip. On a modern system, you can tell the controller, hey, that data I saved in blocks 100 to 125, I don't want that anymore, so you don't need to keep doing read, modify, write, and keeping that around. But the basic interface for SD cards, they don't understand that. That's called trim support. If you've ever seen disk drives talk about trim, then that's basically telling the controller, hey, that whole piece of data, yeah, you don't need to worry about keeping that anymore. So finally, look, some Rust code. This is what the block API looks like. We have a type representing the block, which is of some block length, which is, in my case, always 512 bytes. Then we have a block index and a block count. These are the equivalent of instant and duration in the standard library. One is an absolute value, as one is relative. And I can say, well, you can add two counts together and get another count. And you can add a count to an index and get a new index. But it is illegal to add two indices together because that doesn't make sense. And by using these new types, we can give people an API where it's harder to do the wrong thing. If we just said everything was an int, then it will be much easier to accidentally add two block indexes together. And so our block device trait, we have a read method, a write method, and a way to count how many blocks there are. And this is enough to describe pretty much any kind of disk drive, provided your number of blocks fits into a U32, which I think limits you to about 2 terabytes, but that's fine for now. You could send me a pull request if you really want to make it larger. You'll also note that this is a blocking API. Yes, because I designed this library so that I could rewrite MS-DOS for ARM in Rust, and I'm not interested in the asynchronous API here because my computer has nothing else to do while it's waiting for the disk to read. It's MS-DOS-like. There's only a single task. Many people have asked me, can you do an asynchronous version of this API? And the answer is, I don't know. I don't know how to make this an asynchronous API without taking away kind of that simplicity for the blocking approach. If you have ideas on that, please talk to me later. Or just fork the crate and you can do it yourself. Okay, so we've got this block device API. We want to be able to read and write blocks. How do we talk to the card and do that? Well, you have to send the card various commands. And so if you want to read, then first of all, you need to know if it's a standard capacity or high capacity card. Standard capacity cards use a byte offset. High capacity ones use a sector offset. I guess they realized their mistake and the numbers didn't go big enough. And then you send command 17 to read a single block or command 18 to read many blocks. Yeah, it's kind of annoying. The commands are just numbered, but that's how it is. And eventually the card will send back a response that says, yes, I have prepared the data you have asked me for. And then you say, okay, I would now like that block that I asked for, and it would give you the block and a CRC. You can check the CRC is correct and then eventually return the data. If the CRC is not correct, I guess you could retry. I think I'd probably just panic at the moment and go, no, I don't know, disk is corrupt. That seems weird. It doesn't happen very often. So how do we actually send those commands to the card? Well, we're going to kind of dive down a little bit further. And to send command 17, you need to build an array of 6 bytes. That is the command byte, 4 argument bytes, and a 7-bit CRC byte at the end. And every time you send data over SPI, you send a byte and you get a byte. It's always full duplex. Whenever you send one, you get one back. So we send 6 and discard the 6 we received. And here's where the problem is. There's no interrupt line on an SD card. The only way to know if the SD card has prepared the blocks you asked for is ask it, have you finished yet? And this is like, going on holiday with your kids in the car. Are we nearly there yet? Are we nearly there yet? And is literally, if you ask the SD card too often, at some point it just gets upset with you and stops talking to you. So there's kind of a balance to be found here, because the longer you wait in between requests, the longer you may have to wait for the data to appear. But if you ask it too often, cards just get upset. What is the magic sweet spot? I don't know. I tried all the SD cards I had in my drawer, and I found a number that works. You may try some SD cards, and you may want to propose some different values for how long to wait in between each request there. Then there's the question of, well, how long do you wait? Maybe someone's ejected the SD card and nothing's ever coming back. So again, there's also an upper bound for how long you just keep asking the card. And that also is another reason why this is not an easy thing to do asynchronously, because in an ideal world, you just get an interrupt to say, hey, data is ready, you may read it now. And SD cards, at least with this SPI interface, aren't built like that. But finally, we will get a byte back that begins with a 0 bit, and that is our response, and when we can feed that up the stack. So to talk to the SPI bus, we can use these excellent APIs from the embedded-hal. So if I quit out of the slides, and I should have the docs loaded up. I recommend looking at the embedded-hal docs. I think it's a good example of some really high-quality documentation. Lots of details here about what the SPI bus is and how it works, and the different data types they're offering you, whether you want to talk to the whole bus or just a device. And then the trait they provide to talk to SPI devices looks like this. You can read a number of words. In this case, the word is going to be a byte. You can write, or you can do a transfer, where you're reading and writing at the same time. And you can even transfer in place. So you can send out the bytes and then write the bytes you receive over the top of the ones you just sent. And then the latest version gives you this transaction API. So if there are multiple things you want to do, you can stack them all up in an array of operations, and you can say, hey, do the read, do the write, do the read, do the write, and the HAL will go off and do that for you. And again, lots of lovely documentation that explains in detail how it all works. One of the challenges with this API is SD cards don't work unless you send them 74 clock cycles in advance, and there's no API for sending blank clock cycles without sending data. I used to use the API wrong. People got upset. I've changed it, and I now just have to leave a note that says, I'm sorry, you need to find a way of sending some basically empty data to the card, and you have to do that at a low clock speed. And then once you're done, you can ramp the clock speed up. Okay, so once we've got blocks and we can talk to the SD card, we need a file system. And SD cards are formatted with the FAT file system, which came with this, IBM PC 5150 from 1981. Sorry if you joined halfway through. I snuck in some more computer history. Tough. So original PC-DOS supported only 160K floppy disks, and the file system was kind of designed with that kind of system in mind. I mean, this machine only has like 64K of RAM, I think, if you want the floppy drives to work. No directories supported in the first version. There was just the root directory, and it had files in it, and tough. No subdirectories existed. They were added in subsequent versions. Then it gets interesting around 1995 when Windows 95 comes out. That adds long file names. And then the second version of Windows 95 adds FAT32. Instead of using 16 bits to describe each cluster on disk, it expands it up to 32 bits, and we can now have much larger disk drives. Up until then, we were limited to 2 gigabytes per volume, which wasn't very much. So how does the file allocation table work? There's 2 parts to it. One is the file allocation table itself. It's effectively a linked list of clusters. It's a map, and for every cluster on the disk, there is a word, a 16 or 32-bit word. And if you say, what's in cluster number 25? Then you look in the map and you look at the value for cluster 25, and it says, the next thing in the chain is cluster 50. So then you go and look at cluster 50 in the map, and it says the next thing in the chain is cluster 100. Go and look at cluster 100 in the map, and it says I am the end of the chain. If you've ever done a check disk and it said, oh, found some unlinked chains, then that's because it found some stuff in the file allocation table that didn't have a directory entry, and it just kind of constructed a file based on what it found. Then we have the root directory, which has these directory entries in it, and it tells you, when the file was created. They look like this. I took some hex from literally an image file, and then I manually disassembled it all for you. So you can see we're storing the create date, the modify date time, the access date. Did you know that? Computers keep track on when you last read a file, not just when you last modified a file. And then in the directory entry, we're also storing, how big the file is. If you want to look inside the code, then if we want to read the directory, it looks a bit like this. We make a block array. We call our trait to say, I'd like to read one block, please, and map the error if there's a problem, and then loop through 32 bytes at a time, looking at each 32-byte slice, turn that into a directory entry, and then you analyze it, say, are you the end marker, or otherwise do you match the file name that I'm looking for? And you have to do a linear walk, which is why very large directories on your camera suck, because it's doing a linear walk to find the file name, and every time you want to do the directory listing, you've got to do the whole walk. Modern file systems use trees and work better. I put this code in the slides, and then I thought, yeah, this code sucks, doesn't it? I shouldn't have done that. What I should have done is I should have done this. I should have used chunks exact so we can iterate through 32 bytes at a time. Yeah, see me later. Maybe we'll put in a pull request. We'll make it better. So we said the file names are 8.3. That was the original kind of file name standard from that early PC. So you can have up to 8 characters in the file name and then 3 characters for the extension. And you might be asking, well, how do long file names work? Because there's really only room, wow, these transitions suck, don't they? There's really only room for 8.3 characters in there. So how does that work? Well, what Microsoft did is they sharded the long file name into multiple dummy directory entries, and they store them in front of the actual directory entry. And that allows them to get 13 UTF-16 code units in each block, and then there's a little checksum and sequence numbers, and it's horrible. And I have not bothered implementing it, so tough. You just see the 8.3 version of each file name. And that works fine because it was designed to be backwards compatible. If you delete a file, ScanDisk will clean up after you. If you use my file system, just run ScanDisk on your cards regularly. Don't use it in production. I've had issues in GitHub that said, yeah, I was using your library and my production application occasionally corrupted its log file. And I'm just like, you know I wrote this basically so I could shitpost about MS-DOS. This is not intended for use in production, but I believe in the MIT license when it says no warranty given, express or implied. We then also have an interesting problem when it comes to using the volume manager, which is the thing that manages the mounts. So we can open a volume and open a root directory, and we can open a file, and then we can read and write from the file. But the volume manager is the thing that owns the block device. So for this to work, the file needs mutable access to the directory, which needs mutable access to the volume, which needs mutable access to the volume manager. You can't open 2 files at once, because this is all about exclusive mutable borrowing. So again, I was preparing this slide and I thought, it's not great. I think I'm going to put in a PR which changes it to look more like this, where we're just doing standard shared borrows, and now you can open multiple files at once, but that means the volume manager then needs to have a ref cell inside, and we need to lock whenever we want to do the access and unlock when we're finished. And then if I ever manage to concurrently attempt to lock the structure twice, then they're just going to get a panic, which is suboptimal, but maybe it's better than forcing people to only open 1 file at once. Right, we are very nearly at the end, so just because people complain there's not enough Rust in these computer history talks, let's walk through an example. This is the open directory method. So we pass in a raw directory that is basically a handle to an open directory. Raw directories don't close themselves when you drop them. So this is kind of the lower level API. And then you pass in some name n, where n implements two short file names. So you can pass in strings or you can pass in actual short file name objects, which is what you would have if maybe you were iterating through a directory. There's no point converting to string back again. We keep a little vector of how many open directories we've got. If it's full, we're going to bail out. And otherwise, we're going to say, OK, let's work out what volume this directory is on. Let's go and convert the short file name, and let's go and check. If you are giving the special directory name dot, then I'm going to short circuit the process because you're just opening the current directory. Otherwise, we're going to go and ask the specific file system, hey, please start walking through the dir entry blocks for the directory that starts at this cluster and see if you find any that match. And if they do, great. Otherwise, we can return an error. And then we've got tests as well. And if anybody knows a lot about testing, I'd really love to talk to you, because if I run cargo test, this takes forever because a bunch of my tests work on 512 meg disk images, and I keep them zipped, which means I have to unzip them for every test. But if I run the test cases in release mode, they go relatively quickly. I'm not going to bother doing that. We got one more example to show you, so let's do the shell example. So as a little command line shell, I wrote uses my driver. We've mounted a disk image. We found two partitions inside, and then you can do directory listings, and you can go inside, and you can cat the files, and so on. That is all I've got for you. Please do talk to me later. Check out the docs online. Thank you very much.